I'm going to stay in the bottom corner so I don't cover the graphs for our last set of problems here. We've got two graphs or two reaction energy profiles. Many of these questions aren't directly related to kinetics, but are a good review of chemistry concepts that we will continue to apply throughout the trimester and year. So does the overall reaction absorb or release energy? So we had an uphill and a downhill and ended lower than we started. In terms of our starting position, our delta E, or our energy change is negative. We released energy because the products have a lower potential energy than our reactants. We would define that as exothermic, energy being released. Using kind of the same concept on a smaller scale, which of the bonds, the C to N or the C to C bond, is stronger? And we will have entire units where we're talking about bond strength, but we can also get that from the graph. C to C is represented by this hill on the graph. C to N is represented by this hill. We require a certain amount of energy to break or rearrange that C to N. When we make a C to C bond, which is different right here, it is a different amount of energy. And that hill is larger. So the C to C is more energy because the downhill for the releasing and the forming of that bond is greater than the uphill. We've got our activated complex where we're kind of between the two, but the up and the down are how we can tell the overall energy exchanged. How would increasing the temperature change the value? Once again, a different temperature doesn't change our value of activation energy. That just means that more of our initial reactants are moving fast. Therefore, more of them are going to have the energy required to get over that hill, and specifically the energy required to bend and break that bond. More molecules would exceed the activation energy, more molecules would react, and we would see right here it does change the K. So increasing the temperature changes the value of K because it's not increasing our concentration or doing any other factors that we would find in our rate law, but it does make it go faster. We have to show that in our rate law, so the only way to do that is an increased K. When we change a factor that makes a reaction go faster and the rate is faster, the rate law has to represent that. Catalysts change the value of K. And temperature changes change the value of K because they change the activation energy, or in this case, they change the speed of the molecules. It has all the information within that K beyond what we need to know about collisions and orientation. So that K changes to represent that. Right here, we just asked a simple question because we did a lot right there. I already answered this, but to just restate that, big hills have big activation energies, small hills are small activation energies, and that means the first step is slow, or more correctly, the rate determining step for this. It requires a lot of energy, whereas the other step only requires a little bit, relatively speaking.